Hi. So in this video, we are going to look at a very important proof technique in combinatorics, and that is bijective proofs. So this technique is important for Olympiads in the sense that there are many questions which can be solved by bijective proofs, which are hard to do otherwise. Okay, so let's get into it with this particular question. In a certain part of town, streets form a square grid, and each street is one way and to the north and to the east. So basically, you can only go to the east or you can go to the north from any point, right? So a car is at the northeast corner at 0, 0, and you are supposed to drive to X, which is at 6, 4. So how do we label this? This is, for example, 1, 0. This is 2, 0. This is 2, 1. This is 3, 0, 4, 0, 5, 0, and 6, 0. And this way is +1, right? So 0, 1, 0, 2, 0, 3, and 0, 4. So these are the points on the grid, and you have to go from O to X, right? So how many ways can you go there? So basically, if you think about it, this question boils down to taking 6 east steps, 1, 2, 3, 4, 5, 6 east steps and 4 north steps, right? So in 10 steps, you can reach X. Think about it, you cannot reach X in 9 steps because then you will end up somewhere below or somewhere to the left, right? So you have 10 steps to take, and out of which 6 steps have to be east steps, right? So the number of ways in which you can choose 6 east steps out of 10 steps would be 10C6, right? And the remaining 4 steps will be basically north steps. So in any order, if you choose 6 east steps and 4 north steps, you will end up going to X from 0. So you can think of many paths to do this. One path would be just go first 6 steps is east. So you reach 6, 0, and then last 4 steps is north. So you can go from here to here, right? You can also do 1 step east, 1 step north, 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 then 4 north steps are consumed, and now you have to go 2 steps east, right? So all of these are possible paths, and therefore the number of ways should be 10C6, right? Now, suppose you have to solve the part B of this question. In how many ways can we drive to X if we want to shop at Y 4, 2, right? So first, now you have to reach 4, 2 because you have to stop there. So how many steps are required? 1, 2, 3, 4, and 2 north steps. So 6 steps are there. So 6 total steps, out of which you choose 4 east steps, or you could choose 2 north steps because 6C4 is equal to 6C2. So that makes you reach this Y point. Now, after you have reached this, you still have to go to X, right? So from Y to X, there are 4 steps involved and 2 north and 2 east. So you can multiply with 4C2 because it will be product principle, because first you have to do this and then you have to do this, right? And you have an and statement in between. You have to take both the steps. So it is product principle. So this will be the answer for part B. Okay. So I hope you understood what we are doing here. This seems like a fairly straightforward question. So why are we talking about in the context of bijective proofs, right? So I want you to focus our attention on how we solved this part A, right? So in part A, we had to count possible number of paths from 0, 0 to 6, 4. And we said that this was the same as counting 6 element subsets from the set 1 to 10, right? 1 to 10. Because what we said was 10C6 is going to give us the number, right? So the questions seem totally unrelated, right? Like you are supposed to count number of paths in the real question, and what you're doing to solve it is count how many subsets are possible which have 6 elements from the set of 1 to 10. Here 1 to 10 represent total number of steps, and 6 elements represent 6 east steps, right? So why is this supposed to be equal, right? So I'll write it here. There was a 1-to-1. There was a 1-to-1 correspondence. 1-to-1 correspondence between the set S of all our paths, the set S of all possible paths, and the set T of 6-element subsets, of the set 1 to 10. What do we mean by a 1-to-1 correspondence, right? So in an earlier lecture, we talked about a D-to-1 function, right? So if D is equal to 1, right? 1-to-1 function. 1-to-1 function is a type of function where every element of some set, let's say S, is linked to another element of the other set T, like, and it is 1-to-1. So this is an example of a 1-to-1 set. So if it is 1-to-1 like this, then obviously we can say that mod of S will be equal to mod of T, right? Actually, here, if the function is defined from S to T, you have to ensure that there are no elements left over here which have nothing linked here. So if you know a little bit of theory of functions, so this is called a 1-1 onto function. 1-1 onto function. 1-1, we know what it means. 1-1 means every element here has only one input here. Onto means there is nothing like this. These elements are not allowed, which have no inputs in S, right? So basically, there are equal number of elements in both the sets, and 1-to-1 links are there. That is a 1-1 onto function. Okay. So a 1-1 onto function is sometimes called a bijection. So that is why the title of the video is Bijective Proofs. So what we do here is this. So if the map or mapping or function from f of S to T is 1-1 and onto, then we call it a bijection. When we call it a bijection, if f of S to T is a bijection, what you will have is, then it creates pairs. Matching each element of S, to a different element of T. And basically mod S will be equal to mod T. So an example of a bijection would be something like this: 1, 2, 3, 2, 4, 6. This is a bijection. Each element is mapped to a different element of T, and mod S is equal to mod T, right? And it is a 1-to-1 mapping. This is not a bijection. 1, -1, 2, 1, 2, 3. This is not a bijection, because first of all, it is many to one. For a bijection, it has to be many to one, and it has to be onto, right? So this is also not a bijection. Even if it is 1-1, it is not necessary that it will be a bijection. This is not a bijection, for example, and there's an extra element here. So 1-to-1 mapping was there here, but there's an extra element that has no inputs here, right? So not a bijection, because it is not onto. This function is called an into function, actually. This function is many one and into, and this function is 1-1 and onto. So that is a bijection. So why is this relevant in combinatorial problems? It is relevant because sometimes calculating mod of S directly might be hard, but you could have another set T which is easy to count. T is easy to count. So all you have to do is to establish a function from S to T and to prove that the function is 1-to-1. If you can do that, there is a function from S to T and the function is 1 to 1, then you can say that the number of elements in this is equal to the number of elements in this, right? Once the number of elements are equal, you can just count number of elements in T and that is your answer, right? So this bijection principle is basically a special case of the division algorithm that we saw. Bijection principle is a special case of the division algorithm, where in the division algorithm, if you remember, we had a set where we established a D to 1 mapping, right? Here what we did was we had 1, 2, 3, 1, 2, 3, and these ones were mapped to one element, right? And these were mapped to another element. So this was a 3 to 1 mapping. And then we could say that if this was mod of T and this was mod of S, then we can always say that mod of S is equal to mod of T by 3, right? Here D was equal to 3. For the bijection principle, D is equal to 1, and it is a 1-1 onto mapping, right? So let's try to see how we can apply this principle in actual questions, right? So the first question that we'll look at is, for any positive integer n, for any positive integer n, n, the number of divisors of n, that are greater than root n is equal to the number of divisors that are less than root n, that are less than root n. So we have to prove this statement, that always you will have the number of divisors that are greater than root n is always equal to the number of divisors that are less than root n. So let's see how we will do that. So the first step is, let S be the set of divisors of n that are less than root n, right? Or actually, let's call this one as the greater than root n divisors. And let's say T is the set of divisors of n that are less than root n, right? What we have to do, the strategy in this bijective proof is construct a function from S to T, right? And prove that it is a bijection, right? And prove that it is a bijection. If it is a bijection or 1-1 onto function, then we know that mod S is equal to mod T, right? And then that proves our question, right? So what we will do here is we'll construct a function. Let's say f of S is equal to n by S, right? This function takes inputs S belonging to the set S and outputs n by S, right? Correct. So now how to prove that it is a bijection? Let's think about it. So the first step is, for all S belonging to S, right? The equality S into f of S will be what? It will be S into n by S is equal to n, right? So we have this equality for all inputs S, right? So think about S set here and think about T set here, S set and T set, right? S was the set of divisors greater than root n, and T was set of divisors less than root n, right? So if I have one input here, say S, right? So if I define a function f of S which gives the value n by S, right? Function from S to T which gives the value n by S, you can easily see that if I take an S input, since S is less than root n, when you divide it by n by s, what you will get, the output is greater than root n, right? Think about it. If n was suppose 25 and root n is 5, right? Correct. So s is set of divisors that are greater than root n. Okay, 25 is a bad number. I should take a number which has many divisors. So for example, 60, right? 60 is my n, and root n is what? Root 60 is approximately 7.8 or something, right? 7.8, because 8 square is 64, right? So set of s is the set of divisors which are greater than this. So greater than this is a divisor, could be, s could consist of basically 10, 12, 15, 20, 30, 60, right? And the T set consists of which divisors? 1, 2, 3, 4, 5, 6, and nothing else, right? These are my divisors here, right? Now, what I'm saying is, if my function f of s is n by s, right? So taking any element from set S, if you give an output of n by s, notice that 60 by s becomes an element in this set, right? So if I take 10, so 60 by 10 will be 6, and see 10 is mapped to 6, right? So let me just list out the elements here, right? Let me just list out the elements of s here, elements of t there. So 10, 12, 15, 20, 30, 60. These are the elements of s, and the elements of t are 1, 2, 3, 4, 5, 6, right? So now notice that f of s is such that f of 10 should be 6, right? So 10 is linked to 6. 12 is linked to 5. 15 is linked to 4. 20 is linked to 3. 30 is linked to 2, and 60 is linked to 1, right? This is a function from s to t, and the function is given by n by s. Now you can clearly see here that this is a one-to-one function, right? Every element is linked to one element here, and similarly, there is no element of t that is left behind with no inputs, right? So this is 1, 1 on 2. This is a 1, 1 on 2 function, right? And once you have a 1, 1 on 2 function or a bijection, you can say that mod of s should be equal to mod of t, right? So basically, this can be written rigorously mathematically like this. You have first step is for all s belongs to s, the equality s into f of s is equal to n. Therefore, f of s is a divisor of n. F of s must be a divisor of n because it is multiplied by some integer and it gives n, right? The second step is f of s is less than root n must be true. Must be true, because otherwise what will happen? Otherwise, s into f of s we all know is already greater than root n because it's an element of the set s, and if f of s was also greater than root n, then the output will be greater than n, but that cannot happen because s into f of s is n, right? So f of s must be less than root n, correct? Then we can say that f of s is therefore always an element of t, always an element of t, correct? So f is a function, so we have proved that f is a function from s to t, and the last step is basically we have to show that it is a 1, 1 function. So for all t belongs to t, there is exactly one s, there is exactly one s belonging to s such that f of s is equal to t, right? So there definitely there is one of those s. So for example, if you take t value here, so what is the s value for which f of s will be t, right? So s should be n by t, because then you'll say f of s is equal to n by t is equal to t, right? Let's say s is n by t, right? And this is the only possibility, because if you take another s dash, f of s dash is equal to t, then that implies that n by s dash is equal to t, and therefore s dash is also n by t, but s dash is now equal to s, right? S was n by t, so s dash also has to be equal to s. So you are saying that if there was another element which was giving the output t, that element input must be equal to the original s, right? So this is clearly 1 1. If you're not convinced, look at the diagram that we drew in the previous figure, right? And there it is clear that it is 1 1, right? You can confirm it with different numbers as well. So if it is a bijection, by the bijective principle, we have mod s is equal to mod t. Therefore, we know that the number of divisors which are greater than root n is equal to the number of divisors that are less than root n. So quick recap of the principles involved in the proof. The proof, you have to take set S as one thing that you have to count, and set T as another set that maybe is easier to count, right? And establish a function from set S to T. Prove that the function is 1, 1 and on 2. If you have that, then you know that the elements of set S are equal in number to the elements of set T. So let's look at a few examples to verify this property once more. The question is, the integer, prove that the integer 1000 has exactly 8 divisors, exactly 8 divisors that are larger than root 1000. You have to prove this statement. Now root 1000 is basically 10 root 10, so that is almost 31.62. So our job is to find out how many divisors of 1000 are larger than 32, right? So from 32 to 1000, I have to check which ones are divisors of 1000, right? And I have to count that set. So let's say this set was S, right? S, basically I'll write it properly. S is set of divisors of 1000 from 32 to 1000, right? However, by the previous problem, we know that the number of divisors is going to be the same if you construct a new set T, where T is set of all divisors less than root n, set of divisors less than root n, which is equal to 31.62, then that set has same number of elements as this, right? So therefore now our search can be done in a much easier way, because we have to search only from 1 to 31, right? 1 to 31 we have to search, and that is very easy to find how many factors are there for 1000. We know 1 is a factor, 2 is a factor, 5 is a factor, 10 is a factor, 8 is also a factor actually, 8 into 125, and then you will have 20 as a factor, 25 as a factor, and probably there is one more factor. 25, 20, what else? 16 will be a factor, I think. 16, 8 into 125. No, 16 won't be a factor. Oh, we have missed 4, obviously. 4 is a factor. So we have finished our search and there is no more factors left. And it is much easier to count factors or divisors from 1 to 31 rather than from 32 to 1000, right? So therefore, that is an application of the previous principle only. Let's look at a completely different question now. So the question is this. A new house has 10 rooms. A new house has 10 rooms. 10 rooms. For each room, the owner can decide whether he wants an internet connection, and whether the connection will be high speed or not, whether the connection will be high speed or not. high speed or not. Okay. How many different possibilities does the owner have for all the 10 rooms? How many different possibilities does the owner have for all the 10 rooms? That is the question, right? Now, I don't want to do a direct counting. What I will do is make the claim that the number of possibilities is 3 power 10. And how do I prove that claim? By constructing a function from two sets. So construct a bijective function bijective function from set S, which is the set of all possibilities for the 10 rooms, to the set T of all 3-letter set T of all 10-letter words from the alphabet ABC. So I will make it clear right away. So what we need to do is set S, let's say, is a set of all possibilities for all the rooms. Set T is basically set of all 10-letter words that can be formed from the alphabet ABC, right? Now, this is a very easy question. We have already solved this type of question before. If you have 10-letter words that you have to form and ABC is your alphabet, then each position you have 3 options, right? A or B or C. So 3 into 3 into 3, this is 3 power 10, right? So right away, we know that counting set T is very easy and the number of elements is 3 power 10. The question basically boils down to, can you construct a bijection from this set to this set, right? Can you construct a function from this set to this set? And I will prove here, and this is the function. So let S belongs to capital S. So S is one of the possibilities for the 10-room house, right? One of the possibilities means there are 10 rooms, so you have to tell me whether each room has internet or not, and whether the internet is high speed or not, right? So S is one of those possibilities. So that means that maybe room 1 has internet, room 2 has high speed, room 3 has low speed internet, room 4 has no internet. So one possible enumeration of all the possibilities for the 10 rooms is an element of that set. That is one possibility, that is set, that is S. So let's say we define the ith letter of f of S by this function. F of S ith letter will be A if no internet, will be B if high speed internet, and will be C if low speed internet, right? So basically what we are constructing is a function which takes one possibility from the set S, and for that possibility it constructs a 10-letter word, right? 10-letter word. And how does it construct the 10-letter word? It says if the first room has no internet, then the first letter will be A. If the second room has also got no internet, then second letter will also be A. If the third room has high speed internet, it will be B. So basically we are constructing 10-letter words depending on all of the possibilities. You can easily verify that every possibility has a unique string. Like every possibility, you can check for yourself. Take room 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and say no internet, high speed, low speed, high speed, high speed, high speed, no internet, low speed, high speed. Suppose this is my situation. This is one element of this set. Obviously, we'll construct a unique string of 10 letters for this particular element. So how do you construct? You construct by taking the ith letter. If no internet, then it is A. If high speed, it is B. If low speed, it is C. So then there are 3 more high speed. So B, 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 no internet A, low speed C, C, and high speed D. So this letter will unambiguously tell you, basically without any doubt, looking at this letter and looking at this function, you will be able to say that what possibility we are talking about, right? So this is a clear bijection from this set to this set. And once you have established a bijection, you can say that the number of elements in set S will be equal to the number of elements in set T. And number of elements in set T is just simply the number of possible letters using 3 alphabets and 10 letter words, right? Number of possible words will be 3 part. So that is the answer. So this is a very powerful technique. We will see in the future many more questions where we'll set up a bijection and we'll prove it. So get used to the idea, spend some time on the video, go back, go through it again, and think about how we are approaching it and why it works, right? That's it for this video. I hope you learned something new, and we'll continue with more videos on theory and problems from combinatorics in the future. See you next time.